Alright, so let's continue for our chapter of electrostatics. So, based on the previous video, I mentioned on the description below saying that so let me see. So the previous video we talked about the Gaussian surface application of Gaussian surface in the cubic conductor. So that is actually a mistake. Okay, so let's discuss again about the cubic conductor. So cubic conductor, as I draw from the previous video. So this is we actually call this one as uniform conducting plate. Okay, so this is uniform conducting plate. So based on the plane view of this uniform conducting plate, so what we get is actually this one. So assume our electric field is passes through from the bottom to the above surface of the cubic conductor or the uniform conducting plates. So since the electric field, okay, so since the electric field passes through from the bottom to the above, so it means that the the charge exerted by the surface of the conducting plates, which is the and how should I say? We assume this surface as the plane view of this surface. So the charge exerted by this surface of the uniform conducting plate is actually positive. So the positive, and this is the positive. So this is actually the charge which the uniform conducting plate exerted. So what we need to do is actually find out the Gaussian surface for this uniform conducting plates. Okay, let me erase this one. So our topic for today is actually, so let me see for a second. Okay, so application of Gauss law. Gauss law. Okay. In a uniformly charged conducting plates. So this is actually our aim. So okay, so as I mentioned just now, this is actually a uniform conducting plate. So this is a uniform conducting plate, and which is a cubic rectangular shape. Okay, so in order to find out um, the Gaussian surface for these conducting plates, so what we need to do is actually add the Gaussian surface on the bottom of this surface area. So since the electric field is passes through from the bottom to the above. Okay. Alright, so what we need to do is actually adding a Gaussian surface. So assume my Gaussian surface is actually a cylindrical shape. So this is actually my Gaussian surface. which is a cylinder. So now, for now, my Gaussian surface, the surface area for our Gaussian surface is actually this one. So this one is actually also the Gaussian surface. So what we consider is actually this one, the bottom surface area. So this one is considered to be our Gaussian surface. Sorry, the whole cylinder is actually the Gaussian surface. As for the bottom, the surface area which lie of the bottom of the cylinder is actually the surface area. Alright, so this one is denoted as A. Okay, so based on the so before that, of course, the electric field will also pass through here and here and here. So alright, so this is the electric field. Okay, so what we need to do is actually find out the electric flux which passes through this uniform conducting plates. Okay, so based on the definition of the Gaussian surface, the electric flux is actually equals to the total net charge which exerted on the exerted on this conductor divided by permittivity of free space. Not permittivity of free space, should be the permittivity of vacuum. Alright, so in this case, we assume the permittivity of this cylinder should be the vacuum. So this one is the so for this Gaussian surface or the cylinder, not cylinder. So for the closed cylindrical surface or the Gaussian surface, the permittivity of this Gaussian surface or the cylindrical closed surface is actually the vacuum. So the permittivity of the medium should be the permittivity of free space. So this is the one. Okay, so as for the second one, we know that since the electric field is perpendicular to the surface area, so hence what we have is actually the electric field multiplied by the surface area of the Gaussian surface. So I repeat again. So this cylinder is actually our Gaussian surface, and this surface area is actually the area of the surface area of the Gaussian surface. So this A is actually the surface area of the Gaussian surface, or the closed cylindrical or the surface area of the closed cylindrical shaped Gaussian surface. Okay, so we have 1 and we have 2, and after that we need to equating the both equation. So EA is equal to, so it's not necessary to always to write it as Q net. So what we need to write is actually Q. Okay, so this one is divided by permittivity of vacuum. Okay, so what we have here for the electric field strength, Q is equal E is equal to Q over A epsilon naught. Okay, so So let me just scroll it down. Okay, so as we talked about from the previous chapter, so we know that Q over A is actually equals to the charge density. Okay, so surface charge density of the charge plate. So this is the surface charge density of the charge plates. So what we have here, Q over A is actually sigma over E naught. So if we wish to find out the electric field strength on a uniform conducting plates, so what we need to do is actually for the first step, adding the Gaussian surface. So it's not necessarily always the cylindrical shape. Sometimes you are able to use for, let's say, for another cubic shape. So this cubic shape shall be our Gaussian surface on the bottom of this uniform conducting plates. Okay, so this is for the example. Or if you wish, you can also how should I okay, so actually the surface area should be the bottom instead of sorry, should be at the above instead of the bottom. So this one is so to be note that this surface area is the area that consider the surface area of the Gaussian surface instead of this below the surface area which lie below of this cylinder. Okay, so is there any shape that is suitable besides cylinder? So I think the cubic shape is also suitable. So we know that if we place this cubic shape on the upper part of the uniform conducting plates, so this the surface area for the Gaussian surface that we considered is actually the bottom of this the bottom surface area. Alright, so we have done for this one, application of Gauss law in a uniformly charged conducting plates. Okay, so let me just erase this one. Alright, so this one as well. So let's just move on to the, so let me see for a while. Okay, so let's move on to the electric potential. Okay, let me just use for another color, electric potential. So electric potential, actually we discussed a bit from the previous parts. So in this subtopic, we are about to understand more further. Okay, so before that, what we need to know is actually the definition for electric potential. So what is actually meant by electric potential? So this is C actually. So electric potential at a point in an electric field. So is the work done is the work done in bringing a unit charge from infinity to that point. So electric potential is actually is the work done in bringing a unit charge from infinity to that point. So to be easily to be more specifically, is actually the work done to bring one unit charge from infinity to that point, but in the condition of in the region of electric field. Okay, so electric potential is for the one unit charge. As for the electric potential energy, at a point, of course, this is the condition of electric potential or the electric potential energy. So everything that is related to electric is actually must have this condition, which is in an electric field for anything that related to electric, which is electrostatic force, for example. So this one should be electric potential energy. So same goes to this both electric potential and electric potential energy. So is the work done so is the work oh sorry is the work done in bringing a charge from infinity to that point. So the difference is, so let me just highlight it out. So the difference is the electric potential is only a unit charge. As for the electric potential energy, it's actually a charge. So that's the difference between electric potential and electric potential energy. Okay, so in terms of formula, so what we have here, so let me just erase this one first. Alright, so in terms of formula, okay, so let me just observe for a while. So this is electric potential energy. I'm sorry. So this is actually the electric potential energy, which is U. So U is actually the work done to bring a charge from infinity to that point in the region of electric field. So this is a charge to be noted that this is a charge. So what we have is actually for another one, which is volt, the electric potential. So electric potential is actually describing a unit charge. So what we need to do is actually times the Q, the total charge. So this is a charge, and this is the work done for a unit charge. So a work done for a unit charge times the total charge is what we get is actually the electric potential energy. So this is the relation. Okay, so let's just okay. So from here, what we need to do, what we need to know is actually the direction of the so actually the electric potential does not have the direction, so V has no direction. And to be noted that this electric potential or the electric potential energy, they can be either attractive or repulsive due to the electrostatic force, which can be attractive or repulsive. So this electric potential or the electric potential energy is actually different, how should I say, slightly or totally. So it's actually totally different from the gravitational potential energy and gravitational potential. So this is electric potential can be attractive or repulsive. So the value or the magnitude, whatever for electric potential energy or electric potential, both of them is actually can be positive or negative, depends on the type of charge that carried, depends on the type of charge, the type of charge. So this is one of the important notes that we need to know. Okay, so let's just look back for this one, electric potential. So as I said that electric potential is actually no direction, but it will actually move from higher potential to lower potential. This is always the direction for the electric potential, which is from the higher potential to lower potential. Okay, so let's see. Okay, so let's see what else that we need to know. Alright, so okay, done here. So basically the most important formula is actually Q delta V. So or we can set that, okay, so right, so let me allow me to have some moment. I need to see whether which part that needs to be explained. Okay, done. This one's done. So sometimes the electric potential energy can be explained in terms of W. So W is actually the work done. So actually both of them are same. So this is the important notes. Okay, so alright, so let's look out for the So as I said that both electric potential energy and electric potential can be both attractive or repulsive due to the electrostatic force. So let's check out for the formula. So the formula is actually able for us to show or indicates whether the value should be positive or negative. Okay, so consider I have my electric potential at VA, point A. So I have another electric potential at point B, which is VB. So this is a distance. Okay, so this is my work done. So the work done to bring the charge to move from A to B is actually the VB minus VA. So if the work done to move the charge from point B to point A is actually QVA minus VB. So it is always to remind it's always, how should I describe that? So to be reminded that the change in electric potential must be always final minus initial. Okay, so this is the concept. So this is the electric potential between 2 points. Electric potential difference between 2 points. So what about if I wish to move this charge Q until infinity? Okay, so as I said, the electric potential difference is always the final minus initial. So what will be my final here? So this is actually the V infinity minus VB. So we know that V is actually equals to KQ over R. So if 1 over R, so let's say so 1 over R is approaching infinity. So 1 over R is actually the reciprocal graph. So this is the distance and this is the and this is the distance and this is the electric potential. So the electric potential is actually described in terms of reciprocal graph. So if R is about to approach infinity, so what I can say that my electric potential is actually approaching 0. So the electric potential at infinity, so I can consider it as 0. So this is VB. So what I have is actually negative QVB. Sorry. So what I have to move the charge from point B to infinity, so the work done is actually negative QVB. Alright, so this is the first one. So in contrast, what will happen if I about to move the charge from infinity to point B? Okay, so my work done is actually Q change in potential, electric potential. So as usual, the potential difference is actually final minus initial, which is VB minus V infinity. So V infinity is 0, that we know, VB minus 0. So what I have is actually QVB. So this one is the positive, and as for the previous formula, which is negative, which is to move the charge from point B to infinity. Okay, so let's see what else. Alright, so we have done for this one. So let's move on to another topics. Sorry. Okay. So we're still in the topic of electric potential. So in this case, we are about to see the electric potential which produced by a point charge. So consider I have a positive charge. So we know that the positive charge for the electric field line for the positive charge is always pointing outwards. So this is outwards, and this is outwards, and this is outwards. So consider I have a point A. So we know that this point A is actually inside the region of the electric field which produced by this positive charge. So what we can do, so what we need to do is actually to find out the electric potential which is exerted at this point by this positive charge. So the electric potential exerted by point A exerted. Okay, so let me just modify the sentence. So electric potential exerted electric potential produced by point A sorry, produced by positively point charge exerted by point A so this electric potential is actually KQ over R. Alright, so that's it for this formula. So the electric potential produced by positively point charge exerted by point A is actually the KQ over R. So let's say I have my QP and this one shall be my QP. So since the So since this point A is actually in the region of this electric field, so electric field, so the point A is actually inside the region of the electric field produced by this charge P. So the electric potential is actually exerted by point A is actually KQ P over R. Alright, so I think that's it for the okay. Alright, so there's another conversion need to be done. So remember that the KQ over R is actually equals to QP over 4 pi epsilon naught R. So this is the true formula. Okay, let me erase this one. So we have done for this one. Okay, so as I said that since the electric potential is has no direction, the direction is always from the high potential to low potential. So hence I can conclude that the electric potential is actually a scalar quantity. Okay, so if the case we have the multiple charge which is more than one charge, the charge which is more than one, so the electric potential produced by that multiple charges which exerted by the point A, for example, so it's the sum of the electric potential by each individual charge. So let me give an example. Okay, so let me erase this one. So assume I have multiple charges. So let's say this is the point X. So this is the Q3 and this is Q1 and this is Q2. So both of them, each of them has their both distance respectively to the from the point X to let me just so Q2 has the distance. Okay, let me just change this one. So this is R1 and this is R2. So all of them have their own distance from point X. So since the electric potential is a scalar quantity, so the electric potential exerted by this point X is actually the sum of electric potential which produce. So V is the sum of the electric potential produced by each charges. So I can conclude that my V total is KQ1 over R1 plus KQ2 over R2 and plus KQ3 over R3. Okay, so there's something to be reminded that okay, let me just confirm for a while. So to be reminded that if the Q let's say this is actually the positive and this is positive, but the Q3 is actually negative. So the negative sign for this Q3 is actually must be included. So this one is the negative Q3. Okay, so KQ1 over R1 plus KQ2 over R2 minus KQ3 over R3. Okay, so negative sign shall be included since the electric potential and electric potential energy can be positive or negative, depends on um, the type of charge that exerted in the region of electric field, of course. Okay, so I think that's it for the theory. So let's move on to okay. So let's just move on to the example. So example for the calculation of electric potential is quite simple. So let me see what's the example. So consider I have my Q1. So this is the Q1 and this is the Q2. Oops. And this is the Q2. And this Q2 is actually negative 43 nano charge. So this is positive 67 nano. This is nano column, sorry. So both of them are separated by 1.2 meter. Okay, so the question is find the electric potential exerted by Q2. So it's quite simple that the electric potential exerted by Q2, which is produced by Q1. So what we need to do is actually find out the electric potential produced by Q1, which is V1. So this is KQ1 over R square. Sorry, not R square, should be R. So K is 9.0 times 10 to the power of 9. So the Q1 is actually 67 times 10 to the power of negative 9, which is nano. So divided by R. So my R is actually 1.20. So what I get for the electric potential is actually 502.5, which is volts. Okay, so this is for the electric potential. So what if I wish to find out, okay, let me just write it down. So as for the second question, what if I wish to find out the electric potential energy exerted by Q2? Okay, so this one shall be energy. So the electric potential energy, which is delta U, is actually equals to QV. So this Q is actually Q2 because the aim for us is actually Q2. So Q2 is negative 43 times 10 to the power negative 9 times the electric potential difference between Q1 and Q2. So this is plus 502.5. So what I get is actually negative 2.161 times 10 to a power of negative 5, and this is joule. Alright, so this is how we calculate for the electric potential, both electric potential and electric potential energy. So let's move on to another example. Okay, oops. So let's move on to another example. Okay, let me erase this one. So just now it's actually in the form of horizontal component. What if we included both the horizontal component and vertical component? Okay, so let's say this is my Q1. So my Q1 is actually positive 17 nanocoulomb. Okay, so this is the P, this is the point P, so this is the Q2, so this is negative 53 nanocoulomb. So as for another one, which is Q3, so my Q3 is actually negative 35 nanocoulomb. So all of them has their own distance respectively to point P. Okay. Alright, so let's say this is actually 50 cm, and this is 100 cm, and finally this is 60 cm to point P. Okay, so the question is find the electric potential. So simplified is actually V exerted by point P. Okay, so we know that since the electric potential is the scalar quantity which consists of no direction, so the electric potential is actually the sum of electric potential which produced by the multiple charges. Okay, so the formula is actually KQ1 over R1 plus the KQ2 over R2 plus KQ3 over R3. So my K is actually 9 times 10 to the power of 9. So what will be my Q1? So my Q1 is actually, so this K is actually being factorized. So I left my K outside in this equation. So Q1 is actually positive times 10 to the power of negative 9, 17 times 10 to the power of negative 9. So divided by its distance from point P, which is 50 times 10 to the power of negative 2. So plus the Q2. So the Q2, since the Q2 is negative, so what we have to do is actually add the negative inside the equation. So times 10 to the power negative 9. So the distance from point P is 100 times 10 to the power negative 2. So plus So this same goes to the Q3, which is negative as well. So negative 35 times 10 to the power negative 9. So divided by 60 times 10 to the power of negative 2. So what we have for the final answer shall be the negative 696 volts. Alright, so this is how we find um, the electric potential in form of horizontal component and vertical components. So since the electric potential has no direction, so it's not necessary for us to concern about the resultant electric potential. So this is how the electric potential works. Okay, so let me just write it the final answer. So my V is actually 696 volts, negative 696 volts. So as for the next questions, let me just erase this one first, this one as well. As for the next question, the question actually require for the work done. Find the work done in bringing a charge of negative 40 nanocoulomb from infinity to point P. Okay, so let's say this negative 40 nanocoulomb is actually from the infinity to point P. Okay, so what we need to do is actually find out the work done. So the work done is actually Q and multiplied by the potential difference. So since this Vp, the electric potential exerted by point P, is actually negative 696 volts, so the work done for point P to pull this charge of negative 40 nanocoulomb to point P is actually negative 40 times 10 to the power negative 9 multiplied by the electric potential exerted by point P. So 696. So this is actually positive 502.5 volts. Sorry. This one is not. This one is the. Let me see for a while. Okay. So the answer should be the positive 2.78 times 10 to the power negative 5 joule. So okay, let me just observe for a while. So we know that for this charge, which is, let me consider this one as Q4, and this Q4 is actually came from infinity. So this Q4 is actually not in the region of electric field, not in the region of E. This is because this Q4 is actually came from a point which is much more further from the region of this electric field between which consists of Q1, Q2 and Q3. So this work done is actually done by external force. So we call it this work done as is the work done which is done by external force to move the charge of Q4 to point P. As for if the work is done by the electric field, so if the work is done by the electric field, so usually what we will see is actually negative Q delta V. So this negative is actually the work which is done by the electric field. So if I'm not mistaken, the previous question that we have done is actually negative, which is the electric potential energy. Yeah, the previous question is actually negative 2.161 times 10 to the power of negative 5 joule. So this is the electric field, work done by the electric field, and this is work done by the external force. So that's a difference. Okay, let me just observe. Alright, so let me observe what else. Okay, so I think, yeah, we have done for this electric potential. So let's just move on to the final part of this chapter. So from the previous parts, we actually have discussed about the equipotential body. So in this subtopic, we are going to discuss more further. So actually it is the same. So in this subtopic, we are about to discuss the characteristics of equipotential body or the equipotential surface. So as we know that the equipotential surface, the electric potential at every point is actually the same. So this is 30 volts for this point, and this point is the 30 volts, and this point is the 30 volts. So since the electric potential exerted at any point in this equipotential surface, such as the Gaussian surface, for example, so this one actually is a Gaussian surface. So since the electric potential at any point is equal, so hence the potential difference, which is delta V, is actually equals to 0. So we know that if the potential difference is 0, so the distance so this one is actually the electric field strength. So the electric field strength, let me just rewrite again. So we know that from the previous parts, the electric field strength is actually equals to the negative differentiation of electric potential. Okay. So since there is no change, the change in electric potential in this region is 0, so hence the electric field strength is 0. So this one we know, as we discussed from the previous parts. So for the first characteristics, so the electric potential every point every point of the electric potential are the same. So this is the first one, and we know that the electric field strength is 0, and this is the second one. As for the third one, so since the electric potential is 0, so hence I can conclude that my work done is also 0, which is the electric potential energy. So this work done is actually the electric potential energy, since it is in the region of the electric field. So since the electric field strength is 0, hence the work done is actually 0. So as for the next one, so finally I can conclude that, so since no work done due to the electric potential is 0, hence I can conclude that the electrostatic force which is F is 0. Since no work done, no electric potential, and hence due to the so I repeat again. So since the body is an equipotential, which the electric potential at every point in this region is equal, hence the potential difference is 0. So the electric potential difference is 0, hence the electric field strength is 0. So electric field strength is 0 causes the work done to be 0, since the electric potential is 0. So no work done, hence the electrostatic force in this region is also 0. Alright, so this is the characteristics of equipotential surface. So that's it. I think we'll stop here, and we have done for this chapter. So I'll see you in, if there is any question need to be asked, and please comment below this video. So I'll see you next time. Thank you. Bye.